example 1, we have a gas has initially T1. Let's say the initial state is A. We have TA equals to 200 Kelvin, PA equals 1 ATM, VA equals to 2L. Okay, we have about the units. T must be in Kelvin. P, you can put it in Pascal. 1 ATM equals to 10 power 5 Pascal. And 1 L, 1 liter equals to 10 power minus 3 m cube. So here equals to 2 times 10 minus 3 m cube. This is the initial. I advise you to put all the given and any new result in one table, okay? Especially in the thermodynamics, because you will get a lot of small values. Okay, here we have a cycle. We start by the point A, B, B, C, C, D, D, A. AB, first of all, we have heated the gas at a constant V. When I say heated, it means we have Q hot, Q positive, okay? At a constant V, we have isochoric. To the point B, where T equals to 400 Kelvin. So we can put the values of B, where TB equals to 400 Kelvin, and we have the same volume as A, or at a constant volume. So VB equals to VA equals to 2L. And I don't have the value of PB. Now we go from the point B to the point C, also heated at a constant P. So we have isobaric. We have P constant, so P of C equals to P of D. We can say here C, C equals to 800 Kelvin. We have PC equals to PB, and I don't have the value of VC. Okay, it's a isobaric process. Now we go to the point D by cooling. We have cooled at a constant volume. Cooled, it means we have Q cold. Q must be positive, okay? At a constant volume with P equals to 1 ATM. So at the point D, we have PD equals to 1 ATM. We have the same level as PA. PA equals to PD. And we have at a constant volume. So VC equals to VD. VC equals to VD. And we go from the point D to the point A cooled. So we have a positive Q, and we have T. Okay, we can back to the point A. Okay, so we can back with the point A where T equals to 200. Okay. Okay, first of all, you have to know when we have heated, so we have Q positive. So in general, you know Q AB must be positive, Q, B, C must be positive. When we have a positive Q, we must have a positive internal energy. So delta U AB must be positive, and delta U B C must be positive. Okay, and we have Q C D negative, cooled, and Q D A must be negative. So delta U C D is negative, and we have a negative value of delta U dA. Okay, you have to know all these informations. Just information. Just I want to show here in this problem to resume all these parameters. You know, that's all about delta U. Okay, let's go to the question. First of all, I ask you to show the PV diagram. When I say PV diagram or Clapeyron diagram, what I mean, we have to show all the processes on the PV diagram. Okay, let's go to the solution of the first one. First of all, I start by the point A. You have to know these points. In general, I repeat, in the case of V constant, Q hat, it means P increases and T increases. Cooling, in the case of Q cold, we increase P and we decrease P and we decrease T. In the case of P constant, Q hat means we have to increase the volume, and Q cold means we have a decreasing of volume. Okay, we must have these results when we do the calculation. Finally, you have to get this result. Initially, we start at the point A. At the point A, AB, we have a constant volume. We go from the point A to the point B at a constant volume. So here, in general, constant volume, I have to go up or down at a constant volume. As we have heating, so P must be increased. So we have to go up. Like this, you can know the direction of the path. So here we have Q hat positive. In the case of Q positive, me must be increased. We go to the point B. B to C, we have P constant. So at the point B, we can go to the right or to the left at P constant. As we have Q hat, in the case of P constant and Q hat, volume increases. So we have to go to the right. We go to the right to the point C, where we have here VC and VD. We have the same V. And we have Q hat. Now we go from the point C to the point D at a constant volume. It's a isochoric. We can go down or up at a constant volume. To know exactly the direction, we have Q cold. In the case of Q cold, P decreases. So we must go down. We go to the point D, which has the same P as A. So here we have the point D, and we have cooling, so Q must be negative, and here also we have Q must be negative. Like this, you can know the PV diagram or Clapeyron diagram. Okay, we go to the second question. Here, first of all, how many moles of oxygen are present? We have to calculate N. You know here, quickly, you know N is constant at any point. N at the position A equals to N at the position B, at the position C, and at the position D. You can take any one of these points to calculate N. But as at the point A, we have all the parameters, we have TPV, we can use directly the point A. So here, PAVA, we can say PAVA equals to an RT, N equals to PV divided by RT. You know, P equals to an ATM. You can say 1 ATM or 10 power 5 Pascal. Okay, times V equals to 2 times 10 power minus 3 meter cube, R equals to 8.3, and T equals to 200. We get finally N equals to 0.122 mole. You can add here the given, the result. We have N equals to 0.122 mole. Okay. Second point, what is the pressure at the point P? We have to find PB. If I find PB, you can get PC. PB equals to PC. Here, if you come back to the PV diagram, if you want to find any one of the parameters of B, you can take B and A or B and C. You have to find 2 points to apply the relation between PV, for example. We can take AB. Why? Because at the point C, we don't have P of C. We don't have T of C. So we can take the points, we can take points A and B. You know, PAVA, you know the relation PAVA equals to NRTA divided by PBVB equals to NRTB. We have the same P, so we have the same V, VA equals to VB, NR, we get finally PA divided by TA equals to PB divided by TB. You can substitute the values here. You have PA, TA, you calculate PB, and we have TB. Finally, we get the value of PB equals to 2 ATM or 2 times 10 power minus 5 Pascal. You can write here the value, or here we have PB equals to PC equals to 2 times 10 plus 5 Pascal. Okay. Okay, we go analyze first law for isochoric process AB. What I mean by analyze the first law, you know the first law, delta E equals to delta Q minus d omega. I want to analyze, it means you have to find dQ, delta U, and delta omega. You know, in the case of AB, we have a constant volume. In the case of constant volume, d omega equals to O. And delta Q equals to NCV delta T. Here I give you the value of CV. CV equals to 21.1 joule divided by mole Kelvin. Listen, if you don't have the value of CV, I can give you the value of the adiabatic constant, gamma. In this case, you can say CV equals to R divided by gamma minus 1. Okay? So I give you the value of CV or the value of gamma. Okay. So dq equals to delta U equals to delta NCV delta T. In the case of constant volume, delta Q equals to NCV delta T. You substitute the value of N CV times delta T. Delta T equals to TB minus TA. You calculate the value. As I said before, in the case of heating, delta Q must be positive and delta U must be positive. So we can say here delta U AB equals to plus 514 joule equals to delta Q AB. Okay, next. Here I want to find what is the volume at the point C and D. You know VC equals to VD. Look here. I want to find the volume. We go back to the graph. I want to find VC or VD. So we can take BC, these 2 points, or CD. As we have the values of TB and PB, we can take C and B. So here I take CB, you know PV equals to nRT divided by PV equals to nRT of C. We have the same between B and C with the same P. You can eliminate P and P. We get finally VB divided by TB equals to VC divided by TC. We have VB here equals to 2L. You can put it in L or in M cube times 10 power minus 3 divided by TB equals to 400. VC we have to calculate it, and TC equals to 800. Finally, we get VC equals to VD equals to 4L. So here we can add the value of VC equals to 4L, and here also 4L. Find delta U for the process delta BC. We have to find delta U BC. You know, in the case of BC, we have a constant P. We can back to the constant P. It means delta P equals to O. You know, anyway, in all processes, in the case of T constant, V constant, P constant, we must have delta U equals to NCV delta T. As we have CV, we can apply directly delta U equals to NCV delta T. You know we have the value of N, CV, and delta T equals to T final, TC minus TB. As we have a heating, so delta U must be positive. So delta U BC equals to 1028 joule. Okay. Find d omega of the case BC. You know, omega equals to the integral PDV. This is the expression. You can use it directly. As we have a constant P, you can put it outside. So we get here P integral dV between the point B and C. So equals to P V final VC minus VB. We have the value of P equals to 10 power 2 times 10 power 5. We have VB, VC, and VB times 10 power minus 3 to get m cube. We get finally 405 joule. This is delta omega. We can put it here. Delta omega BC equals to 405 joule. Listen, anyway, between B and C, the volume increases. In this case, we must have a positive value of omega. Okay, so it must be positive because we have an expansion of volume. Okay, it's here. Volume increase. In this case, we must have a positive work. And this work is provided by the gas. Volume decreases, so the work must be negative, and this quantity is received by the gas. When I say provided, it means it must be positive. When I say received, it must be negative. Okay. 8. Find delta Q for BC. We have to find delta Q BC. You come back to BC. In the case of BC, we can solve the problem. You can say, as we have a P constant, you can say NCP delta T. Okay, NCP delta T. If you have CP, you can apply directly. But we don't have delta T because I don't have the value of TD. So we cannot use NCP delta T. Okay, for example, you know delta Q equals to NCP delta T. We have, in the case of P constant, BC, N is given, CP you can calculate it. Why? Because we have CP equals to CV plus R. We have R, we have CV, we can calculate CP, but delta T equals to T, D, T. We have TC. Okay, we can use it. You can use this one, okay? We find CP and delta T equals to TC 800 minus 400. We can calculate the value of delta Q by using this expression. Okay, or as we have delta Q equals to delta U plus d omega, I want to calculate, I have delta U BC equals to 1028. I have the value of d omega calculated before equals to 405. We calculate dq, it must be positive. We have heating equals to 1433. Okay, this is the value of delta Q BC. Joule. And okay, we write here. What is the value of TD? I want to calculate TD. Also, we come back also to this one. I want to find a value of D. You can take 2 points, B, C, or B, C, D, or DA. It's the same. We have all the, we can use the path from D to A or from C to D. Anyway, I take the path from C to D. You know PV equals to nRT. We have the same volume. We can eliminate the volume. We get finally PC divided by TC equals to PD divided by TD. We have the value of PC, TC, PD, and we get finally the value of TD, which is equal to 400. So we can write here TD equals to 400 Kelvin. So it's very important to put all the results here. It's clear. You can solve any one directly. Okay. If you let me eliminate this one before. Okay. Uh, Analyze first law of isochoric process CD. I mean, we have to find delta Q CD, delta U CD, and delta omega CD. Okay. You know, CD, in the case of CD, we have a constant volume. So delta U, delta Q equals to NCV delta T, and delta omega equals to O. As we have the value of CV, you can apply directly to calculate delta Q. You know, delta U equals to delta Q minus the omega. As we have the omega equals to O, delta U must be equal to delta Q equals to NCV delta T. We have NCV and delta T equals to T final TD minus TC. You get finally the value of delta U and delta Q. As we have a cooling from the point C to D, so delta U must be negative and delta Q must be negative. So here we have delta U CD equals to minus 128, which is equal to delta Q. Okay. Find delta U of dA. In the case of dA, we have a constant P. Okay, you can use directly delta U equals to NCV delta T. I said before, you can use it in all processes. So we have N, we have this one, and this one. You can calculate delta U. dA equals to 1 minus 514 joule. Find the omega of dA. You know, in the case of dA, we have a constant P. We can put it out. So we have PdV equals to P V final minus V initial. We have P, we have D and VA and VD, and you get finally a negative value. Why? Because we decrease the volume. So omega must be negative. The work done by the gas must be negative. Okay? Finally, find dQ of dA. Anyway, in the case of dA, we have a constant P. We can use delta Q equals to NCV delta T. We can calculate Cp equals to Cv plus R. We have this one. We can calculate Cp, which is joule divided by mole Kelvin. Okay? So delta Q equals to NCp delta T. Delta T equals to TA minus TD. We can calculate it. Or we can use the first law of thermodynamics equals to delta U plus d omega. We have the value. No, be careful. Here, delta U equals to delta. No, it's okay. It's okay. So we have the value of delta U and the omega. So finally we get a negative value of delta Q as we have cooling. Okay.